Remember this moment exactly as it is. In a few seconds, you will leave Earth in your mind and begin a slow journey through the asteroid belt and the family of dwarf planets that share your sun. All you need to do is listen and let yourself drift away from your familiar room while we focus on one simple task: assembling a clear, gentle picture of these distant worlds for you. For the next while, you are no longer just a viewer. You are a passenger on a quiet spacecraft that slips out of Earth's shadow and sets a course for the asteroid belt and the dwarf planets beyond Mars. This entire video is your personal flight. We will explain and compare, and you will simply watch these small worlds from the front row of your window seat. Outside your window, Earth slowly shrinks into a calm blue circle, wrapped in a thin halo of atmosphere and cloud. City lights fade into a soft, speckled glow. The engines are almost silent, just a gentle vibration under your feet as we guide the ship outward. Above you, space is dark and steady, and ahead, a faint band of scattered rocks waits in the distance. Tonight's quiet question is simple: why is there a broad ring of rocky fragments orbiting between Mars and Jupiter, instead of another full-grown planet like the one you are leaving behind? As your spacecraft glides outward, we will trace the story of those fragments, and of the dwarf planets that keep them company on the edges of the solar system. To understand what you are flying toward, you quietly slip backward in time. In your mind's eye, the neat orbits vanish, and the young sun glows inside a broad disk of gas and dust. About 4.5 billion years ago, everything you see tonight, from tiny grains to dwarf planets, was part of that hazy, swirling cloud wrapped around a newborn star. From your seat on the spacecraft, you imagine that disk as a slow, foggy river of material. Tiny particles bump together, stick, and grow. Over millions of years, they build clumps called planetesimals, bodies big enough for gravity to round their shapes and pull in more debris. In some regions, these clumps merge into full planets. In others, the growth is interrupted. Your course tonight takes you to one of those interrupted regions. Between the young orbits of Mars and Jupiter, countless planetesimals tried to come together. But Jupiter's growing gravity kept stirring the area, gently tugging and pulling on orbits so often that no single world could dominate. Instead of one planet, the result was a scattered family of rocky leftovers. For a long time, scientists wondered whether the belt was the shattered remains of a lost world, a planet that formed and then somehow broke apart. As you drift outward, it is easy to imagine a missing sphere where your path now leads. But modern measurements show that the belt's total mass is far too small. It is not a ruined giant, but material that never quite finished growing. If you could collect every asteroid in the main belt and compress them into one body, it would be less than 5% of the Moon's mass. From your window, that fact gives the region a different feeling. You are not entering a crowded junkyard of broken worlds, but a delicate, low-mass ring of survivors, fragments that preserve early conditions in the solar system. As the spacecraft glides farther from the Sun, you will pass through zones where the nature of these fragments slowly changes. Closer in, many asteroids are rich in silicate rock and metal. Farther out, darker, carbon-rich bodies dominate, containing primitive material that has changed very little. Astronomers group them into types, each one a different clue to the early disk. Most of these objects are irregular, their gravity too weak to pull them into perfect spheres. A few, however, are large enough that their own weight has rounded them. When a body reaches this kind of balance, scientists may call it a dwarf planet. From your seat, that distinction matters, because it marks the boundary between small fragments and almost planets. Among the many rocks ahead, one stands out as your quiet destination tonight: Ceres, the only dwarf planet in the main asteroid belt. Roughly 950 kilometers across, it is big enough to be nearly spherical, yet small enough to share its orbit with countless neighbors. As your course aligns with it, you begin to sense its subtle pull on your journey. Long before your imagined spacecraft, Ceres was discovered from a quiet observatory on Earth. On the first day of 1801, the astronomer Giuseppe Piazzi noticed a moving point of light in the gap between Mars and Jupiter. At first, many hoped it was the missing planet that mathematical patterns had hinted at. Instead, it became the first sign that this gap held many small worlds. In the years that followed, more faint travelers appeared in the same region: Pallas, Juno, Vesta. What seemed like one new planet turned into a growing list of tiny bodies. The astronomer William Herschel suggested calling them asteroids, meaning star-like, because they were points of light in his telescope. From your vantage point now, they are no longer points, but landscapes. Your flight carries you into this once mysterious gap. Instead of a smooth, unbroken orbit, you move through a region quietly shaped by chance, gravity, and time. The intrigue that first drew astronomers here still lingers. Why are some bodies like Ceres nearly round while others remain jagged fragments, and what secrets about water and early chemistry might they still hold inside? As you look outward, imagine a temperature map painted across the early disk. Close to the newborn sun, most ices could not survive, and rocky planets like Mercury and Earth began to grow. Farther out, beyond a line where it stayed cold enough, ice could join rock and dust. Many asteroids in the outer belt, and Ceres itself, likely formed from this colder, more water-rich material. Ceres seems to have taken a small but important step toward planethood. From your window, you can picture it forming as a mixed ball of rock and ice. Heat from radioactive elements and impacts slowly melted some of that ice, letting heavier rock sink inward and lighter materials rise. Over time, this gentle separation created layers, giving Ceres a more complex interior than many asteroids. Ceres is not alone in this halfway category. Far beyond the belt, dwarf planets like Pluto, Haumea, Makemake, and Eris circle the Sun in the frozen outskirts. You will visit those distant regions in your imagination later, but tonight the focus stays here, in this middle band, where one dwarf planet shares space with millions of smaller fragments inside the orbit of Jupiter. As your ship approaches the main belt, a gentle surprise greets you. It is not the crowded minefield you might picture from movies. Space here is still immensely wide. Most asteroids are separated by millions of kilometers. You might drift for days without passing a large body. The belt is a statistical crowd, not a literal one, a broad region where orbits simply favor small worlds. Yet even in this wide quiet, patterns appear. As we guide your path across the belt, we avoid certain orbital distances where Jupiter's gravity would nudge your course again and again. In the real belt, those repeated tugs clear out swaths called Kirkwood gaps. They are invisible lines in space, where long-lived asteroids rarely remain, carved by the rhythm of a distant giant planet. From your front row seat, the idea that Jupiter both prevented and shaped a planet's birth starts to sink in. The same gravity that protects the inner solar system from many incoming comets also kept the material here from merging into one sphere. Instead, it turned this region into an archive of building blocks, each asteroid carrying its own record of the solar system's early days. You now glide through an area that once saw far more activity. In the early solar system, leftover planetesimals crossed paths, collided, and sometimes were thrown toward the inner worlds. Some scientists think there was a period of especially intense impacts, a late heavy bombardment, though details are still debated. Either way, fragments from this region often visited the young Earth and Moon. Pieces of these objects still arrive today as meteorites, small stones that fall through Earth's atmosphere. In laboratories, researchers examine their minerals, trapped gases, and tiny grains older than the Sun itself. From your quiet seat in space, you can imagine holding one of those samples in your hand, a cooled remnant of the same processes that shaped the belt around you. Many meteorites, especially those from dark, carbon-rich asteroids, contain hydrated minerals and organic compounds, signs that water once flowed through their parent bodies. Some scientists think that objects like these may have delivered part of Earth's water and some of the ingredients for life. As you drift past them tonight, they are quiet, but their chemistry hints at a lively past. From your seat above series, you let that gentle thought about Earth's water deepen. You are drifting in a quiet cabin, but in your mind the clock begins to run backward. The oceans on the blue world behind you shrink and vanish, the continents glow red, and the familiar planet dissolves into something far more raw and unsettled. You watch as Earth rewinds past mountains, forests, and dinosaurs, past the first cells stirring in ancient seas, back to an age when there were no oceans at all, only a young, molten world wrapped in a choking atmosphere of steam and gas. For a while, it is hard to believe that this blazing sphere in your calm, ocean-covered home could ever be the same place. In this early scene, most of the water is trapped as vapor in the thick, hot air or locked deep inside the planet's rocks and minerals. The surface is a restless ocean of lava. Meteorites and comets still fall more often than they do today, flaring briefly in the sky before splashing into molten rock. The world is loud, bright, and unstable, yet even here the ingredients of future oceans are gathering. Now you let the movie play forward again, just more slowly than before. The crust begins to cool. The glowing seas of magma darken and solidify. Steam in the atmosphere condenses into clouds. Rain starts to fall, not a gentle drizzle, but relentless storms that can last for thousands of years. Water pools in the lowest basins, then spreads, until the first true oceans begin to form. From your window above Ceres, you imagine those new oceans as a dim, iron-tinted mirror wrapping a still hostile world. The sky is thick and reddish, lit by a sun that shines dimmer than today. Volcanic islands break the surface here and there, venting gases and metals into the air and sea. Around the planet, impact craters mark where incoming bodies kept arriving, stirring the surface and adding fresh material. It is in this unsettled era that the belt you are drifting through now finds its quiet way into Earth's story. Asteroids from the outer, darker regions, rich in water and carbon, wander inward, their paths nudged by Jupiter's tug and by subtle resonances. Some miss the inner planets entirely, slipping back into the dark. Others strike the moon, carving the great basins you can still see through a telescope. And some hit Earth. You follow one of these travelers in your mind. For millions of years it has circled the sun as a modest carbon-rich rock, perhaps a few tens of kilometers across, one of countless fragments that never became a planet. Inside it, minerals cling to water, and simple organic molecules hide in microscopic pores. It is entirely lifeless, yet already carries some of the chemistry that life will later borrow. A small change in its orbit, an ancient collision, a distant nudge from Jupiter, sets it on a slow inward slide. Orbit by orbit, it crosses paths with Mars, then with Earth. When it finally meets the young planet's atmosphere, it arrives as a streak of fire. The energy of impact is enormous. Rock, water, and organics are blasted into vapor. A crater opens, and shock waves race around the world. From your seat, it sounds violent. And it is. Large impacts can melt rock and sterilize entire regions. Yet not everything is lost. Some of the water in the incoming body stays bound in minerals or is added to the atmosphere and later rains out. Some of the carbon-bearing molecules survive and mix with Earth-made organics, adding variety to the growing chemical soup of the early oceans. Now you zoom out again, watching not just one impact, but thousands spread over hundreds of millions of years. Some scientists picture a particularly intense phase of bombardment, others see a more gradually tapering rain of bodies. Either way, compared to today, the sky of early Earth is busy. Each bright streak marks another small delivery from the broader solar system. You imagine the cumulative effect. A drizzle of carbon-rich asteroids over a vast stretch of time adds up. Each one contributes a little more water, a little more carbon, a little more nitrogen and phosphorus, ingredients that life uses in every cell. The oceans deepen. Their chemistry grows more complex. Earth's own interior outgasses water and volatiles as well, but the belt and its cousins are adding their quiet share. Back in the present, scientists on that blue world try to measure this hidden delivery with careful tools and patient experiments. They compare the ratios of ordinary hydrogen to its heavier sibling, deuterium, in Earth's oceans to the ratios in different kinds of meteorites. Some of the darkest, most primitive meteorites, fragments of carbonaceous asteroids, carry water whose fingerprints closely resemble those in your seas. From your orbiting cabin, you picture a researcher peering into a tiny vial of melted meteorite, analyzing its isotopes. If the match is close, it suggests that at least part of Earth's water once rode inside these small, dark bodies from the belt. It does not prove that all of your oceans came from this source, most likely they did not, but it ties a portion of every wave and raindrop to the region you are drifting through now. Asteroids do not deliver only water. Inside some meteorites, scientists find simple organic compounds, amino acids, ringed carbon molecules, and other chemical pieces that can participate in prebiotic reactions. These are not signs of life, but they are evidence that carbon chemistry can become rich and varied even on small, cold worlds. When such material falls into warm ponds, tidal pools, or deep ocean vents, it adds new layers to the unfolding chemistry. From your vantage point, you imagine an ancient shoreline under a sulfur-tinted sky. Waves lap at volcanic rock. Lightning flashes in the clouds. In the water, molecules made on Earth mix with those delivered from space. Some are broken apart, others joined together. On the seafloor, near hot vents, minerals catalyze reactions, building and rebuilding complex structures. No one can say exactly how the first self-replicating systems arose, but the ingredients are everywhere. Those ingredients are what connect your quiet flight through the belt to every living cell on Earth. The carbon in your body may come from multiple sources, but some fraction almost certainly passed at least once through dust grains, planetesimals, and asteroids before reaching the planet that would host you. The same goes for trace metals like nickel and cobalt that enzymes rely on. You are, in a very literal way, made from recycled small worlds. You let that idea settle in. The asteroid belt did not simply throw rocks at Earth and walk away. It acted as a kind of long-term delivery system and mixer, sending in pulses of material that helped set the planet's inventory of water and biologically useful elements. Even now, tiny grains from asteroids and comets still drift down as micrometeorites every day, maintaining a quiet connection between your biosphere and the space beyond. There is another, subtler way this region shaped life's story, by influencing which impacts did not happen. Jupiter's gravity, the same force that stirred the belt and prevented a full-grown planet from forming here, also acts as a gatekeeper for the inner solar system. Many objects from the outer reaches that might have plunged toward Earth are instead diverted, captured, or ejected into interstellar space. From your seat, you can imagine two versions of the early solar system. In one, giant planets sit in different orbits, stirring the belts more violently or less efficiently. Maybe the inner worlds are bombarded so often and so hard that any emerging biosphere is repeatedly wiped out. In another version, almost no small bodies ever cross the paths of the rocky planets. Earth forms dry and chemically simple, with few deliveries to spice its oceans. The real solar system lies somewhere between these extremes. Enough impacts occurred to bring water and complex chemistry, to churn the crust and open new habitats, but not so many that the surface stayed molten and lifeless forever. From your window, the belt looks sparse and calm, yet its long-term pattern of impacts helps set the delicate balance between destruction and opportunity on your home world. Even much later in Earth's history, this balance continued to shape life. You think of the impact that ended the age of dinosaurs, carving a crater off the coast of what is now Mexico and triggering a wave of extinctions. Its exact origin is still studied, but its chemistry and orbit hint at links to the outer asteroid belt. A single rock from that wider family rearranged the tree of life, clearing ecological space for mammals, and eventually for you. It is a sobering thought, but also a reminder that the story of oceans and life is not smooth. It is punctuated by rare, powerful events that redirect evolution. The belt and its cousins have been part of that punctuation from the beginning. Without them, Earth's biosphere might have followed a completely different path, or never started at all. You let your attention drift back to Ceres, turning slowly below you. Its dark surface, bright salt deposits, and hints of buried brines are suddenly more than scientific curiosities. They are examples of what a nearly planet can do with water and rock when given billions of years and a modest supply of heat. In some ways, Ceres is a small, frozen echo of processes that played out on a grander scale on early Earth. Imagine, for a moment, a world where bodies like Ceres were more common, or where a Ceres-sized object had formed closer in and collided with Earth at just the right time. The delivery of water and salts would have been different. Ocean depths, salinity, and the distribution of elements might all have shifted. The exact recipe for habitability is sensitive to details like these, details written in the scattering of small worlds. From your quiet orbit, you start to see the asteroid belt less as an accident and more as a kind of archive of near misses. Each fragment is a record of a path that material might have taken, into a planet, out of the system, into a moon, or into an impact. By studying this archive, Ceres included, scientists on Earth are reconstructing how many different ways there are to make oceans, atmospheres, and possibly life. You also see how this local story echoes outward to other stars. The dusty belts astronomers detect around young suns might be playing similar roles, feeding water-rich bodies into the inner regions, carving craters on forming planets, sowing organic molecules in newborn seas. Somewhere, on a world you will never visit, another ocean might be thanking its own version of an asteroid belt for existing. In the cabin, you breathe in and out, feeling the slow rhythm of your own body. Outside, in your mind's view, Earth's oceans glitter in sunlight, stitched together from steam rising out of volcanoes, from icy comets, and from countless carbon-rich asteroids whose journeys began in the same broad ring of material you are passing through now. The salt on your skin after a swim, the water in your tea, the rain that taps on windows, each carries a faint, unbroken line back to these small, persistent worlds. For a moment, you let that connection be simple. The asteroid belt is no longer just a ring of rocks. It is a long-lived participant in Earth's story, a quiet sculptor of oceans and a patient supplier of the raw materials for life. You are not just leaving it behind on this imagined flight, you are acknowledging it as part of the deep ancestry of everything that swims, grows, and thinks on your planet. When you are ready, you can let the view outside your window widen again. Ceres shrinks to a dot, the belt softens into a faint band, and the blue of Earth brightens in the distance. You carry with you now not only a map of orbits and missions, but a more intimate understanding. The water and life you know so well are, in part, gifts from this quiet ring of unformed worlds. Ahead of you now, Ceres begins to resolve from a pale point into a small, ghostly disk. Its surface is mottled with craters and gentle variations in color. You notice that it is darker than Earth's moon, reflecting only a small fraction of the sunlight that reaches it. Against the deep black of space, it looks like a dim, rounded ember left glowing in the solar system's hearth. Scientists have measured Ceres's mass and size and found that it is less dense than pure rock, but heavier than solid ice. From your seat, this translates into an inner picture, a mixed body with rock concentrated toward the center and icy, salty materials nearer the outer layers. It is a compromise between a dry, rocky asteroid and a fully icy world from the outer reaches. There are hints that, long ago, Ceres may have hosted pockets of liquid water beneath its crust. Radioactive heat and the slow decay of aluminum and other elements could have warmed icy layers enough to melt them into salty oceans. Today, any such water would likely be briny and scattered, but subtle features on the surface suggest that brines have reached up and refrozen more than once. As your spacecraft draws closer, you notice bright patches standing out against the dark ground. These are deposits of reflective salts, likely left behind when salty water reached the surface and evaporated into space. One large crater, named a crater, hosts a cluster of these bright areas. They shimmer faintly in the sunlight, like frost catching the dawn on a distant, airless plain. From your window, Ceres begins to feel less like a random rock and more like a preserved experiment in planet building. It is large enough to have differentiated, to sort its materials and perhaps sustain internal water for long spans of time, but small enough to avoid full geological restlessness. In its quiet way, it holds clues to how water and rock interacted in the early solar system. Not far away, another large body, Vesta, tells a contrasting story. It is smaller than Ceres but denser and more strongly layered, with a basaltic crust formed from ancient lava flows. Meteorites from Vesta have been found on Earth, letting scientists match rocks in our laboratories to features seen from space. From your ship, these two worlds become a quiet pair of case studies in early geology. The line between asteroid and dwarf planet is not drawn by size alone. By current definitions, a dwarf planet orbits the Sun, is massive enough for gravity to make it nearly round, and has not cleared its orbital neighborhood of other bodies. Ceres satisfies these conditions, while Vesta does not quite reach roundness. From your seat, you are watching that boundary play out in real objects. As your flight levels off near Ceres's orbit, you can sense that our naming schemes are still catching up with reality. Dwarf planets are scattered through different regions, one here in the belt, several far beyond Neptune, and perhaps more yet to be confirmed. The solar system is not just 8 major planets with crumbs between them, but a spectrum of sizes and histories filling the gaps. Later in this journey, your imagination will carry you to those outer reservoirs, the Kuiper belt and beyond, where dwarf planets are colder and more distant. For now, you remain in this middle zone, circling a small, round world that formed close enough to the Sun to keep some rock, yet far enough to preserve water and salts. It is a middle child in distance, size, and composition. Ceres itself has moved through several roles in human understanding. After its discovery, it was briefly counted as a planet. As more objects were found in the same region, it was reclassified as an asteroid. Only in the early 21st century, when astronomers refined the categories of planets, did Ceres become officially known as a dwarf planet, a small world with its own quiet dignity. From your calm vantage point above Ceres, this change in labels is a reminder that science is a moving conversation. As measurements improve, categories adjust to match nature more closely. The first wave of tonight's intrigue is not about drama or danger, but about how many more worlds like this might be waiting in the data, ready to reshape our picture of the solar system once again. As your ship coasts in the gentle arc of Ceres's orbit, the scene feels peaceful, but the questions are deep. How much of Earth's water, and how many of the molecules that later assembled into life, once resided in small bodies like this? Did fragments from this belt help shape the oceans and chemistry of the planet you left glowing behind you at the start of this flight? For most of history, these questions had to be asked from far away, through telescopes that saw Ceres as a tiny, shimmering disk. Only recently have spacecraft traced careful paths through this region, mapping surfaces, measuring gravity, and sensing subtle variations in composition. In the next stretch of your journey, you will follow those paths more closely, from your quiet seat by the window. For now, you simply drift alongside Ceres, letting the dwarf planet slowly rotate beneath you. Craters turn like slow hours on a stone clock, and the sun is a distant, steady lamp. Between your ship and the faint glow of Earth, the asteroid belt stretches in a wide, sparse band. You are suspended in its middle, held gently between past and possibility. As you drift above Ceres, held in a slow arc of orbit, you are looking at a view that took generations to earn. For most of human history, worlds like this were nothing more than pinpoints, their details blurred into starlight. To feel how far our understanding has come, we can let your spacecraft trace the path of our telescopes and probes, step by gentle step, through time, down on Earth. Centuries before your quiet flight, astronomers pressed glass into lenses and mirrors, trying to sharpen the sky. Early telescopes showed the moon's craters and Jupiter's bands, but the tiny bodies between Mars and Jupiter remained faint, moving sparks. Their orbits could be traced on paper, yet their true shapes and surfaces stayed hidden from view. As instruments improved, astronomers began to record asteroids on photographic plates, tiny streaks sliding across crowded star fields. By measuring how quickly they brightened and dimmed as they rotated, researchers could infer rough shapes and spin rates. Light curves became clues, turning simple changes in brightness into hints of elongated forms, tumbling rocks, or nearly rounded bodies. Prisms and spectrographs added color to this story. By splitting asteroid light into its component wavelengths, astronomers learned that not all of these objects were alike. Some reflected light like stony silicates, others like metallic iron and nickel, and many showed the dark, muted signatures of carbon-rich material. From Earth, chemistry began to emerge from specks of moving light. Over time, patterns in those spectra led to families: bright, stony S-type asteroids more common toward the inner belt, darker C-type bodies dominating the outer regions, and rarer metallic M-type scattered among them. These trends hinted that temperature and composition during formation still shaped the belt today. Even before spacecraft arrived, observers could sketch a rough chemical map. Careful tracking of orbits added a second layer of insight. When astronomers plotted thousands of asteroid paths, they noticed clusters with similar shapes and tilts, as if shards from a single shattered parent. These asteroid families suggested ancient collisions, events so distant in time that only their statistical footprints remained. The belt began to look like a slow, ongoing experiment in breakup and mixing. From your quiet orbit near Ceres, we let the view widen in your mind. The dwarf planets and asteroids you have visited become small beads on invisible threads of gravity, all circling the same star. As you zoom out in imagination, the belt is northwest longer and isolated place, but one layer in a larger design that links your own world to the farthest icy outskirts. From your seat at the window, you picture the solar system as a series of zones frozen in time. The rocky planets close to the sun, the belt of leftover building blocks, the giant planets farther out, and the distant icy ring all formed from the same disk. Asteroids and dwarf planets preserve pieces of that disk that never melted or merged. Like fossils scattered in orbit, you notice how the main belt sits between two kinds of worlds. Inside its orbit, Mercury, Venus, Earth, and Mars are mostly rock and metal. Beyond it, Jupiter and Saturn are giants wrapped in thick envelopes of gas, and the ice giants Uranus and Neptune carry large stores of water, ammonia, and methane. The belt marks a boundary where conditions shifted during formation. Scientists think that in the early disk there was a snow line, a region beyond which water could stay frozen instead of boiling off into gas. Inside that line, rocky planets formed from dry material. Outside it, ice could join the mix, helping giant planets grow quickly. Ceres orbits close to this boundary, and its mixture of rock, ice, and salts reflects that in-between position. From your quiet vantage point, you consider the water flowing on Earth. Its origin is still under study, but clues hide in the ratios of different forms of hydrogen and oxygen in oceans and meteorites. Some asteroids, especially dark carbon-rich ones, carry water locked into minerals with similar chemical signatures, hinting that they may have helped fill Earth's basins long ago. It is a gentle but deep thought. The same collisions that scarred the Moon and battered young planets may also have delivered vital ingredients. Large impacts could be devastating on short time scales, yet over millions of years the steady rain of smaller bodies may have supplied water, carbon compounds, and metals that helped make your own world habitable. Your flight now turns your gaze outward beyond the Sun. Astronomers have found planets orbiting many other stars, and in some systems they also detect broad bands of dust and rock. These debris belts are inferred from faint excesses of infrared light, the glow of warm grains too small to see directly. They may be distant cousins of your asteroid belt and Kuiper belt. Powerful radio arrays, such as large millimeter-wave observatories in the southern hemisphere, have imaged young stars still wrapped in disks. You can imagine those views on your screen, bright rings and gaps carved into dust by forming planets. Your own belt seems like the long-settled remnant of a similar stormy youth, now quiet enough to drift through in your mind. From your seat, you call up the paths of dwarf planets far beyond Neptune. Many of them travel in resonant patterns with that planet, completing a set number of orbits in the time Neptune finishes a different set. Pluto, for example, circles the Sun 2 times for every 3 circuits of Neptune. These ratios act like fingerprints of an earlier era when the giants slowly migrated. One widely studied idea is that the giant planets did not always sit where they are now. As they interacted with the surrounding disk of smaller bodies, they traded angular momentum and shifted their orbits. In the process they scattered countless icy planetesimals outward and inward, reshaping the Kuiper belt and sending comets toward the inner solar system. Your quiet flight through the main belt now feels different. The gaps in asteroid orbits and the families of fragments are not random, they are traces of Jupiter's strong gravity and of possible past wanderings. If the giant planets had moved in a different way, the belt might have held a full planet, or perhaps the inner worlds would have been too disturbed to remain stable. From your seat at the window, you extend this thought to other planetary systems. Some stars host giant planets that sweep close to their surfaces, bodies larger than Jupiter skimming nearer than Mercury orbits in your own system. In such arrangements, it may be harder for small rocky planets to keep gentle, stable paths. Your solar system's layout suddenly feels more precious. You remember that the iron in your blood and the calcium in your bones were forged in ancient stars, then built into dust, rocks, and finally planets. Some of those atoms may once have passed through asteroids and dwarf planets before settling on Earth. As your spacecraft glides above Ceres, you are, in a quiet way, looking at distant relatives of the matter that became you. The small bodies under and beyond your ship act as time capsules. Their craters, compositions, and orbits preserve conditions from epochs long before any life stirred on Earth. You cannot travel back to those early days, but by reading these clues you reconstruct how gas and dust settled, how ice and rock combined, and how a young system gradually separated into planets and belts. From the front row of your spacecraft, this story loops gently back to the room where you are resting. Each meteor shower you might one night watch through a window is a brief, bright trace of material related to these belts and streams. The streaks burn away in seconds, yet they connect your sky to the long, quiet history of collisions and orbits you are drifting through now. As your ship holds its steady path, the third and deepest question arrives almost on its own. You are a conscious observer riding inside one small planetary system, built from the same processes you have been watching. If similar belts and dwarf planets circle many other stars, how many other places might be piecing together their own stories about origins and connection right now? For the moment, no answer is needed. You simply float with your spacecraft above Ceres, surrounded by paths of worlds that tie the inner planets to the distant ice. In the final stretch of your journey, we will turn from the grand pattern back to the present, to the scientists and explorers now studying these small worlds, and to the quiet futures they are beginning to imagine. New techniques joined the picture. Radar signals bounced off nearby asteroids revealed sizes and rough outlines. Infrared telescopes measured their heat, helping to estimate diameters and how dark or reflective their surfaces were. Piece by piece, from flickers of light and faint echoes, scientists turned anonymous points into objects with real dimensions, temperatures, and textures. From your seat above Ceres, you can imagine all that careful work pooling together on desks and chalkboards. By the late 20th century, astronomers could describe the belt in broad strokes, its chemistry, its families, its zones of stability and absence. Yet no telescope, no matter how sharp, could match the simple clarity of flying right up to these worlds and looking down. That wish quietly guided mission planners. In the 1990s, a spacecraft named Galileo, bound for Jupiter, was steered past 2 asteroids along the way. It flew by Gaspra in 1991 and Ida in 1993, sending back the first close-up images of main belt bodies. For the first time, asteroids appeared not as dots but as irregular, cratered landscapes beneath a passing robotic visitor. As Galileo slid past Ida, it revealed an unexpected companion, a tiny moon now called Dactyl, circling its host like a pebble bound to a larger stone. That single discovery showed that even small asteroids could have their own satellites, hinting at complex histories of capture and collision. The belt, once imagined as simple debris, was already proving more intricate than expected. Your spacecraft now echoes the path of later probes. In 2000, the Near-Shoemaker mission slipped into orbit around the asteroid Eros, mapping its grooves and boulders in detail before gently touching down. Images showed a rubble pile world, likely assembled from fragments, its surface littered with rocks the size of houses. Asteroids were no longer abstract hazards, but specific, studied places. Japan's Hayabusa missions and NASA's OSIRIS-RX went further, not just visiting small bodies but briefly landing and collecting material to bring home. From Itakawa, Ryugu, and Bennu, they returned grains and pebbles that scientists now examine under microscopes. These samples carry records of heating, water alteration, and organic chemistry, turning distant rocks into tangible pieces of solar system history. From your quiet window above Ceres, all these earlier encounters feel like previews, brief glances that prepared us for a longer stay. Each mission refined techniques for navigation, imaging, and sampling. Each one confirmed that small bodies preserve diverse stories, some melted and refroze, some stayed primitive, some were assembled from shards. Together, they pointed toward more ambitious goals. One of those goals was to visit not just small asteroids, but the larger survivors that almost became planets. In 2007, NASA launched the Dawn spacecraft, equipped with efficient ion engines that glowed with a soft blue exhaust. Dawn's mission was unusual, to orbit 2 different bodies, Vesta and Ceres, and compare them directly as relics of the early solar system. Dawn arrived at Vesta first in 2011, easing itself into orbit with long, gentle thrusts. From close range, Vesta's surface revealed deep troughs, towering cliffs, and a vast basin near its south pole, evidence of a colossal impact. Its basaltic crust confirmed that it had once been hot enough for lava to flow, behaving more like a small, frozen-in-time protoplanet than a simple rock. After more than a year at Vesta, Dawn slowly spiraled away and set course for Ceres. Its ion engines whispered continuously, trading power for patience as it climbed outward through the belt. In early 2015, the spacecraft slipped into orbit around the dwarf planet that now turns beneath your imagined ship, becoming the first mission to visit a dwarf planet up close. Once captured by Ceres's gentle gravity, Dawn settled into a series of progressively lower orbits, circling again and again. From high altitude, it mapped the global shape and gravity field, showing that Ceres is slightly flattened and denser toward its center. These measurements supported the idea of a differentiated interior, with rock concentrated deep inside and lighter, icy material above. Closer in, Dawn's cameras revealed a landscape of craters and smooth plains, but one feature drew immediate attention: brilliant spots inside a crater, shining against the dark ground. Early images left their nature uncertain. Were they ice, salts, or something else? As better data arrived, scientists saw that these patches were highly reflective deposits on a slightly raised central dome. Spectrometers on Dawn helped resolve the mystery. The bright material matched the signature of sodium carbonates and other salts, minerals that form when salty water evaporates. This suggested that, deep below, Ceres still hosted reservoirs of brine that occasionally rose through fractures. Even a modest, frozen world could drive slow, long-lasting chemical circulation, far from any star-warmed ocean. Dawn also mapped subtle variations in gravity and topography, revealing places where the crust seemed softer or more buoyant, perhaps supported by pockets of liquid or slushy ice. A solitary mountain, a Hanuman's, rose from relatively smooth terrain, its flanks streaked and young. Many researchers interpret it as a cryovolcanic dome, built by the slow upwelling of icy, salty material from below. From your orbiting seat, these findings quietly shift how you see Ceres. It is no longer just a cold relic, but a place where internal heat, water, and salts have interacted over billions of years. While no one expects lush ecosystems here, the presence of long-lived brines shows that even small bodies can host sheltered environments where complex chemistry has time to unfold in the dark. Dawn even detected localized patches of organic-rich material near some craters, including one named Ernetet. These organics are simple compared to the molecules of living cells, yet their presence on Ceres, alongside water and salts, strengthens the idea that the building blocks of life are widespread. Your view of this small world now includes not only rock and ice, but subtle chemistry as well. While Dawn orbited Ceres, other tools were changing what we knew about dwarf planets far beyond. Powerful ground-based observatories and the Hubble Space Telescope found icy bodies orbiting in the Kuiper Belt, a distant ring beyond Neptune. Some of these objects, like Eris, were similar in size to Pluto. Their discovery forced astronomers to rethink what counted as a planet at all. In 2006, the International Astronomical Union adopted a definition that distinguished full planets from dwarf planets. To be a planet, a body had to orbit the Sun, be nearly round, and clear its neighborhood of other objects. Pluto and Ceres met the first two criteria but not the third, joining a new category of dwarf planets. Labels shifted, but the worlds themselves remained unchanged in the dark. When New Horizons flew past Pluto in 2015, it performed for the outer solar system what Dawn had done for Ceres. Blurry dots turned into detailed landscapes, a vast, bright heart-shaped plain of nitrogen ice, dark equatorial regions, and jagged water ice mountains rising like frozen cliffs. Thin hazes layered the sky. A distant dwarf planet proved far more active and varied than many had expected. Pluto's large moon Charon and its smaller companions also showed surprising features: canyons, smooth plains, and hints of past resurfacing. Crater counts suggested that some terrains were geologically young on cosmic timescales. Together, Ceres and Pluto challenged the idea that only big planets can stay active. Even modest worlds, if they retain internal heat and volatile ices, can keep evolving quietly. Other distant dwarf planets, though not yet visited by spacecraft, have revealed themselves through careful observation. How may a spin so rapidly that it is stretched into an elongated shape and appears to have a faint ring? Makemake reflects sunlight from icy methane on its surface. Eris orbits even farther out, in a path that carries it through some of the solar system's deepest cold. When these remote bodies pass in front of background stars, brief dips in starlight, called occultations, reveal their sizes and sometimes their atmospheres. This is how scientists inferred Pluto's thin envelope of gas and Haumea's ring. From far beyond your Ceres orbit, another layer of measurement flows in, showing that even the faintest dwarf planets can be weighed and outlined with precision. Up here above Ceres, your spacecraft becomes a kind of bridge between all these efforts. The images, spectra, gravity maps, and star-dimming events gathered over decades flow together into a single mental model. You are watching one dwarf planet directly, while holding in mind a growing family of others, each one extending the theme: small worlds can be complex, layered, and surprisingly active. Large survey telescopes have multiplied the known population. Infrared missions like WISE and its NEOWISE extension scan the sky, detecting the heat of asteroids that visible light surveys might miss. Ground-based projects such as Pan-STARRS, and in the near future the Vera C. Rubin Observatory, repeatedly map wide fields, catching new moving points and refining countless orbits in the background. These surveys show that the family of small bodies is far from complete. Hundreds of thousands of asteroids are catalogued, yet many more remain too small or faint for current instruments. In the outer solar system, only the brightest dwarf planets have been firmly identified. Somewhere beyond Neptune, additional round worlds may be circling quietly, still hidden in the crowded star fields. With each new discovery, some questions narrow while others widen. Measurements of meteorites and icy surfaces help trace possible sources of Earth's water, yet no single population of objects seems to tell the whole story. Ceres, Vesta, Pluto, and the Kuiper Belt dwarf planets each show different balances of rock, ice, and organic material, like variations on a theme we still do not fully understand. Scientists now ask how long subsurface oceans or brine layers can persist inside small worlds, and what controls their chemistry. Does a thicker shell of ice insulate liquid longer? Do pockets of ammonia and salts lower the freezing point enough to keep fluids moving? From your orbit, these questions drift through your mind like distant signals, gentle and unresolved but rich with possibility. Ceres itself continues to give up its secrets slowly. Dawn's mission ended in 2018, but its data live on in archives that researchers still explore. New analyses of gravity, composition, and crater patterns refine estimates of how thick the icy shell might be and how recently brines reached the surface. Even after the spacecraft fell silent, the dwarf planet's quiet story keeps unfolding on computer screens. Meanwhile, new spacecraft are being sent toward other small bodies. NASA's Lucy mission is on a long tour of Trojan asteroids that share Jupiter's orbit, while the Psyche mission is heading for a metal-rich object that may be the exposed core of a protoplanet. Each of these targets samples a different layer of planetary building blocks, adding contrast to the picture that Ceres has helped start. From your calm vantage point, the second wave of intrigue becomes clear. Small worlds are no longer supporting characters in the solar system story. They are archives of its earliest chapters, test cases for how planets do and do not form, and laboratories for water and organic chemistry. Each new mission answers a handful of questions while quietly writing a longer list for the future. As you continue circling Ceres, the motion feels smooth and repetitive, but the ideas are expanding. The instruments that once flew here, the telescopes scanning from Earth, and the surveys of distant dwarf planets are all converging on a larger question. In the next part of your journey, you will follow that question outward, connecting these modest bodies to the wider architecture of the solar system. After sitting with that realization for a while, you feel your spacecraft begin a slow, deliberate turn. The nose tilts slightly inward, toward the Sun and the inner planets, even as you remain above the soft arc of Ceres's orbit. Your journey is still outward in thought, but in space your path is starting to trace the long curve home, gentle and unhurried. Below, Ceres continues its patient rotation, and far beyond it the dwarf planets follow their elongated tracks around the Sun. Around you, unseen radio waves and silent laser pulses from Earth still sweep through space, carrying data, commands, and questions. You are sharing this quiet region with a web of attention stretching from observatories and missions back on your home world. On the ground, teams of scientists and engineers are still decoding what earlier spacecraft have seen here. Dawn's maps of Ceres and Vesta are re-examined, pixel by pixel, to refine models of their interiors. New techniques tease out subtle hints of buried brines, crust thickness, and ancient impacts. Even long after a mission ends, its images keep giving up fresh layers of meaning. In laboratories, thin slices of meteorites are polished, etched, and scanned at microscopic scales. Within them, researchers trace tiny veins filled with minerals that only form in the presence of liquid water, and grains that preserve isotopic fingerprints of early solar system environments. Each fragment becomes a miniature probe, complementing the wide-angle views from orbit that you have imagined tonight. The story of small worlds is also continuing through new missions already in flight. One spacecraft is on its way to explore a metal-rich body named Psyche, which may be the exposed core of a once larger object. Another, called Lucy, is looping outward to visit Trojan asteroids that share Jupiter's orbit, sampling a population that has been largely untouched since the era of planet building. Together, these missions extend the work that began with visits to Eros, Itakoa, Ryugu, Bennu, Vesta, and Ceres. From your seat, you can imagine the slow arcs of their trajectories weaving through the inner and middle solar system like careful brushstrokes. Each one is aimed not at spectacle, but at answering precise questions about composition, structure, and history. Other spacecraft, such as New Horizons, continue to send back data from the distant Kuiper belt, refining our picture of Pluto and its neighbors. Ground-based telescopes monitor occultations when dwarf planets pass in front of stars, using the brief dimming to measure sizes, shapes, and even thin atmospheres. The result is a steady, gentle tightening of our understanding, rather than sudden shocks. At the same time, surveys of near-Earth asteroids quietly map and track objects whose paths bring them close to our planet. Radar reflections and precise orbit calculations help identify which bodies simply pay harmless visits and which require careful watching. The focus here is not on fear, but on knowledge and preparedness, turning uncertainty into measured awareness over many years. From your vantage point in this imagined cabin, you can sense how these efforts fit together. Detailed maps of Ceres, Vesta, and the Kuiper belt dwarfs tell us how small worlds store water, ice, and metals. Meteorite studies and comet samples show how those materials move between regions. Orbit surveys and models connect all of it into a dynamic picture of a living planetary system. Future explorers may someday use this knowledge in practical ways. Water bound in minerals and ice inside certain asteroids could be turned into drinking water, breathable oxygen, or even rocket propellant. Metals concentrated by ancient melting and differentiation could supplement scarce resources on Earth. From your quiet seat, these ideas feel like distant, slow-moving possibilities rather than urgent plans. Before any such use, though, there is a more immediate and universal benefit. By understanding how belts and dwarf planets form and evolve, scientists refine the broader rules of planet formation. Those rules are then applied to planetary systems around other stars, helping to interpret faint clues from debris disks, exoplanet orbits, and subtle variations in starlight. Large observatories, including upcoming facilities designed to map the sky again and again over many years, will notice new asteroids, distant dwarf planets, and perhaps additional bodies with sizes between Ceres and Pluto. Each discovery will slightly adjust the census of our solar system. From your spacecraft, you can picture a quiet scroll of newly plotted orbits spreading across a dark screen. This is one reason astronomers sometimes say that the solar system is still under construction, not in its positions but in our understanding. For centuries, maps showed only a few planets and a blank space between Mars and Jupiter. Now that gap holds Ceres, Vesta, and a host of families, while the outer darkness has blossomed into a rich catalog of icy worlds and dwarf planets. As your flight continues, you might notice how this evolving picture has changed the way people talk about what a planet even is. The reclassification of Pluto and Ceres sparked lively debates, not because these worlds changed, but because our categories had to stretch. In the end, the existence of dwarf planets made the solar system more varied and interesting, not less. From your window, labels begin to feel secondary. Whether we say planet, dwarf planet, or asteroid, each body is a specific landscape with its own gravity, chemistry, and history. Science needs categories to organize knowledge, but the worlds themselves simply follow the paths that physics and time have given them. Your spacecraft honors that by lingering, looking, and listening without haste. In a broader sense, the study of these small worlds also influences how you see Earth. When you compare its stable oceans and thick atmosphere to the bare rock of Vesta, the salty scars of Ceres, and the frozen plains of Pluto, you get a clearer sense of just how many conditions must align to produce a planet where liquid water can persist on the surface for billions of years. You also see that Earth is not a sealed system. It shares material with the rest of the solar system through meteoroids, comet dust, and the occasional larger impact. The metals in your technology, the rare elements in electronics, and even some of the water in your glass are connected to processes that played out across belts, dwarf planets, and long-vanished planetesimals. As your ship gradually arcs inward, the sun grows slightly brighter in your forward viewports, and the belt begins to thin behind you. Ceres recedes into the dark, becoming once again a modest point of light amid many. You carry its story with you now, not as a distant trivia fact, but as part of the larger narrative of how complex worlds and conscious observers arise from simple beginnings. Soon, Mars and then Earth fall back into your mental frame. From this imagined distance, your home planet looks like just one more object on a chart of orbits. Yet you know that down on that small blue world, air moves in gentle currents, clouds form and break, and countless lives unfold, including yours, existing for a brief moment on a timescale that these rocks would barely notice. In the cabin, almost all motion has become slow and repetitive, indicator lights pulsing, the faint hum of systems, the soft suggestion of a window frame around the stars. Your body is resting wherever you are listening from, while your attention drifts between Ceres, Pluto, distant belts, and the familiar pull of home. Nothing in this scene demands effort. You are simply present with it. As we bring this journey toward a close, you can let the main thread settle in your mind. You began near Earth, rose outward through the orbit of Mars, and entered the wide, surprisingly sparse ring of the asteroid belt. You visited Ceres, watched Dawn's findings unfold, and then extended your gaze to distant dwarf planets and the belts and disks around other stars. You followed the growth of our understanding, from early telescopic points of light to flybys, orbiters, and sample return missions. You traced how asteroids and dwarf planets connect to Earth's water, to organic molecules, and to the long-term stability of planetary systems. You felt how these small worlds, though modest in mass, play an outsized role in the story of habitability. Now your imagined spacecraft is quietly aligning itself with a homeward trajectory. Outside, the sun, the belt, and the dwarf planets remain exactly as they are, continuing their slow turns whether anyone watches them or not. Down on your real planet, you are lying or sitting in a comfortable position, breathing in and out at a pace that feels natural, with nothing you have to do. If your eyes are still open, you can let them rest a little more, knowing that the story will keep running in the background of your thoughts. If you are already drifting into sleep, the details of Ceres, Pluto, and the asteroid belt can fade into a soft blur, like distant stars viewed through a slightly fogged window, still there but no longer asking for your full attention. You can remember, if you wish, that this flight is always available to you. On another night, you might rejoin this quiet ship and glide once more through the gap between Mars and Jupiter, or continue outward to explore other families of small worlds. Or you may choose a completely different journey through the cosmos. The universe holds more than enough stories for many peaceful nights. For now, though, you have reached the gentle end of this particular path. The asteroid belt, Ceres, and the dwarf planets return to their places in the dark, orbiting in silence around a star that has been shining for billions of years and will shine for billions more. You remain on your small, living world, with your breath, your heartbeat, and all the time you need to rest.